So, uh, natural language processing enables computers to understand human language. And I just showed us human language. This is human language. These are English alphabets. These are English sentences. We have different human languages. We have Russian, we have German, we have Igbo, we have English, um, we have Portuguese. We have different languages. We have different languages, and those are human languages. So when we go back to our slides, when we say computers, NLP enables computers to understand human language, it means we can teach computers to understand every single language, and that can be seen in Google Translate. I can go to my Google Translate. I can go to my Google Translate, and in this Google Translate, in this Google Translate, I can choose this. I can type something in English. Good morning. I'm using a machine, and this machine is and then I'm using my own laptop, my own computer, and but it has been programmed to understand this human language. They can translate human language. You can translate from one human language to another. I can translate this to Arabic, and this is in Arabic. I can translate this to Spanish. This is Spanish. Um, Buenos dias. I can translate this to many human languages. You can see human languages, many human languages, as many as possible. And the more AI tools we have, the more people are trying to translate human languages. You can see not many languages. I can see my own language over here. You can see many languages here: Japanese, Romanian, many human languages here. I can translate it to French. I can translate it to Russian, to many languages. Let me see, because I've been there. I can just translate it to something else, like say Russian language, and that is going to be, where is Russian? It's going to be Dobre Otro. So you can translate many things. So this is part of what we are talking about. So this is NLP. The machine is able to translate good morning to Russian, and so I can understand this. And let me try. Well, that's I don't want to spend too much time, so I'm going to spend less time on that. But I believe you understand what we mean by what we mean by um, NLP, natural language. Is natural language. Is a language. Why is it natural? It's something. Um, they are natural languages. So when we talk about NLP, natural language processing, we're talking about the languages. Um, we're talking about the languages that we have. The languages that I showed you there. Those are natural languages that we have. And then these natural languages cuts across different fields. You go to journalism. Journalism, they're also using languages. You can translate the language in journalism to something um, that the machine understands. You can translate something. We have, when we come to biology, in biology we have something, let me go back here. In biology we have things like nucleotides. If you're in biology or chemistry, you understand when we talk about nucleotides, well, it's going to translate it to this, but you know the standard nucleotides we have. Can you list the standard nucleotides? If you're in biology, maybe you'll get some points, extra points. List the standard nucleotides we have in the comment box. Let's see if you know the standard nucleotides. Standard nucleotides. You can list the standard nucleotides in the comment box. Standard nucleotides. Do we have biologists here? Do we have biochemists? Do we have people in the medical allied sciences, bioinformatics, chemistry, standard nucleotides? So I just want to let you know that the standard nucleotides that we have, because I was taking a little bit more time, I'm going to leave that, but I'm going to show you that um, we have DNAs and RNAs, and from DNA and RNA we have thymine, we have uracil. Thymine is from DNA, uracil is from RNA, and then we have the other nucleotides. I believe you all can mention them now. We have um, cytosine, which binds with either T or U, and then we also have okay, is adenine. Let me put that first. Is adenine that binds to T or U, and then we have C, which is cytosine, which binds with what? Um, Cytosine binds with what? All right, binds with what? And what type of bond does it maintain? Okay, oh, someone listed them here for us. Guanine. So cytosine binds with guanine. So those are standard nucleotides that we have. So this binds with okay. So and you can see these are natural language. These are alphabets. This English alphabets. And in many languages, this is what we have. So even biology language is a natural language, and that's why we can actually model nucleotides as a problem. We can model it as a natural language. And when we come to tokenization, I will show you how we break it down into different things. Like we break the T T that binds to U, and this to G. We can see how that works. But you can see I just gave an example of in biology that this is also natural language. So our DNA and our RNAs, they are all natural language. They are part of natural language. I mean, based off the letters that we have, because they are natural letters, and so it's part of the natural language. So this is another clear example of natural language. And so I will go back to my slides, not slides, well, the 10 points that I once I establish these 10 points, you should be able to understand. And on our slides, we're going to be very fast, but I believe you understand. You now know what is machine learning. That's AI is machine learning. So when we talk about AI is the umbrella, and then machine learning is a section of AI. We're going to talk about that when I move to my slides. But at least you know what these two when we talk about these two, you know what they mean. And then we have word embeddings. Word embeddings is simply converting text to meaningful letter numbers. Converting text to meaningful numbers. So computer understands numbers. It doesn't understand letters. Computer doesn't understand text. So whenever you have text, you have to convert it to numbers. And for some of you, you did this right in secondary school or your high school. You did this. You know that computers only understands numbers. So I give an example. I was talking about this here. I think let me go back to my example. You see, this is this. If I want to feed these standard nucleotides, and in some cases they have N, which it's like on. It's just it can be anything. It can be any of those other nucleotides, but if I want to feed this into my model, my computer doesn't understand nucleotides. It doesn't understand letters. It doesn't understand words. My the computer only understands numbers. Like I can start with 0. I can say I can convert this and say let my t be 0, and let my u be 1, let my a be 2, and let my c be 3, let my g be 4. So in this case, I've ended up splitting these standard nucleotides. I mean, converting these standard nucleotides, which were words, which were letters, I mean to say, into numbers. These are numbers. So when you convert those letters into numbers, you're simply embedding. And when you do it in other ways, we have different encoding. We call it, you encode. So you are encoding text to numbers. If I don't want to call embedding, I'll call, because this is natural language. So in natural language, we call it embedding. So when you hear about embeddings, if you've been dealing with machine learning and all you know is one hot encode, or like in after one hot encode, if in biology, you know um, you know um, uh, commands. So it's just similar. It's similar to that. But when you look at deep learning, it's one hot encode that you convert your data, your data that is not numeric, your categorical data. We have numeric and categorical. Categorical is what we are calling your. It could be male or female, male, female, and you can't feed male or female into your model. So you can say let male be 1, let female be 1, and let male be 0. And with that, you can be able to feed that into your model. So the same way you do in deep learning and you do in other aspects, and tomorrow you're going to be dealing with machine learning and all this, and you'll be able to learn more on that. But the same way you have one hot encode in deep learning is the same way you have embedding. So it's just a different way of calling that here in natural language processing. So when you hear about this, that shouldn't be something too difficult for you. It's just simply converting text to numbers. If you understand the first 3, type a plus in the comment box. If you don't understand, type a minus. If you understand the first 3, type a plus. If you don't understand, type a minus. All right. So it seems you understand this well. So I'll go back to where I was showing you this, and then we'll keep. Now we have attention mechanism. Now we have a paper that came out in 2017, and that paper was called "Attention is All You Need." And the attention is all you need. You don't understand number 2. All right, number 2 is simply number 2. I think I spend more time on number 2, which is simply I'm speaking English, and that's a natural language. So when we talk about natural language processing, you're processing this natural language we're talking about. I gave an example here where we try to process a natural language. We try to convert it. Let me copy this because I will still need this. We processed something like good morning. This is a natural language. You are giving good morning. This is a natural language. You are giving it to the computer. And the computer is able to process this natural language. That's the NLP, natural language. This is a natural language. And the computer is able to process this natural language into something else, into another language. And in this case, Russian. We can say Russian. Dobre utro. And it can convert this to something like I love my mom. Ja lubię swoją mommy or mamu. You see, it's been a while and I'm forgetting all my Russian. But you see, it's converted that to that, or maybe something like um, my country is Nigeria. You see, Maya strana Nigeria, Maya strana Nigeria. So this is converting this. This is processing. The computer is processing. So the computer is able to understand this natural language. So computers are trained. They are trained to understand this language, and that is what we're calling natural language processing. So if the computer is trained to understand this language, it can also be trained to understand the biology language. And that's where I came to this, that we can actually train a computer to understand the biology language, and it can be able to solve problems for us. We've trained the computer to understand natural language, to understand English, and be able to convert whatever we type in English to Russian. You can see this is in English, it's able to convert it to Russian. So it's the same way you can do that. So but because of time, I'll be moving on to the next, and I'll also talk more about that when we come to the slides. But I just want to highlight these 3 takeaways, and at the end of this class, you should be able to understand these 10 points. So attention mechanism, just as the name implies, we have what we call attention mechanism. When you hear about ChatGPT, a paper that came out in 2017, attention is all you need, is what brought us to where we are in AI today. It changed the whole game. Attention is all you need. It helped us to focus. It helps us to focus on the relevant parts of a text or of an input. You can give an input to the model, and using the attention mechanism, you are able to focus on only the most important parts. For instance, I give an example, and because I'm from the medical allied sciences, and I do understand that this is biology, and that my DNA is that DNA is my genetic makeup. DNA contains my genetic makeup, and because DNA contains my genetic makeup, it can be able to. I have um, I have some segments of the DNA that that contains the most relevant information. It contains the most relevant information, and that part of the DNA that contains such kind of information is called what? Who will tell us that part of DNA? That part, it may not just only be DNA, but that part that contains the relevant information is called what? Um, okay, let's see if someone will get it. If someone from biology will get that point again. Um, all right. While we wait for that, okay, someone is giving us gene. This is much deeper than gene or nucleus. It's much actually deeper. Chromosomes. Okay. Someone is giving us chromosomes. Um, yes, gene contains. Yeah, gene is is cool, but there's something I want us to go downstream and look at the DNA sequence, and let's see what we can get from there. All right, it's motifs. Motifs. So the motifs are very important. Whenever we're talking about the functionality of that, those are segments of the DNA that are very important. So you may have a very long sequence, you know, and you want to focus on some maybe some regions that um, have the most important motifs for maybe a particular disease or maybe something function. So you may ask the model, to focus on those relevant parts. And also, you may have a video like now I'm speaking, and maybe at some point I wasn't making sense because I was too low or my explanation was very poor, and maybe you were not able to get my explanation. So the parts you didn't get, if you want to rate me, you will rate me based on the parts you were able to understand. For instance, someone say, I don't understand the second point. So if you are to rate me, you're going to focus on the parts that you understood better. So that's the attention you are giving to my talk, to my presentation, to my teaching. You are focusing on what you understand. That's the attention. You are giving the attention to what you got out of this class. You know? So that's the part. So by so doing, you focus on the relevant information. So the motif, for instance, I gave an example. The motifs are the most important, the relevant parts of the DNA. I mean, the DNA sequence. If I'm working with motifs, if I'm working with a DNA sequence, and I want to maybe condition my model on something, and I'm looking for a very important or biological functionality, I'm going to focus on the motifs, or maybe something like binding or something. So I'm going to focus on the most important parts of of my DNA. So and then we'll talk more about that. You see more examples, but then we also have transformers, which also revolutionized NLP. I'll be talking more about that. Transformers and attention mechanism, they work hand in hand, and is what you have, what was used in training ChatGPT. So with this combo, with this attention mechanism and transformers, ChatGPT came to be. And then all the AI tools you see today, they came out because of this natural language processing, and not only natural language processing, but because of the attention mechanism and transformer models. And what they do is they employ masking. Masking works in such a way that you can. This is how ChatGPT works, and this is how the technology works. You can have a word say, I love my mom. So if I say I love my mom, um, you can mask some words like this. Let me mask this. That's locking. You lock this. I'm locking this. Just know that this is locked. That's not this like this. The model is not seeing this part of the sentence, and this is called masking. I just masked, and during COVID, we're all on masks. We're all masking so that we will not get COVID. You know, so 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 you're masking this. So your model is learning. Can your model predict something that is missing here? Can your model predict something that is missing here? And it has been trained such that it's able to understand that even if I miss something here, that's why when you misspell things in ChatGPT, it's still able to correct it and give you the right answer, because the model has been trained in such a way. We may not have more time to go in depth, but do understand that we are just introducing you to the terminologies and just to understand the very basics. That masking is done such that if you make a mistake, that's why in coding, I use Cloud, and if I make mistakes on Cloud, let me go to my Cloud, and I type something like teach me attention. Now look at what I'm typing. I'm sort of like omitting things here, but you see, I'm going to omit some. You can see this is not attention, and I'm going to I'll omit some words in transformers. Transformers 2, I will miss. You can see this is not the correct one, but you can see I've missed a lot of words here. But once I type this, it's able to understand the whole sentence. Why? Because it has been trained to do that. So what is attention? It's going to give us examples. Attention is allowed a model to focus on different parts of the input when processing each word. So it focuses on different parts. It calculates to know the attention scores. We call it attention scores. And then instead of treating all input equally, it learns how much to focus on each position. And it is giving us examples. But you can see, was that what I gave to the model? No. I omitted a lot of things here. They were not correct. But why is he able to know this is what I'm talking about? Because it has been trained to understand that. And how now can we be able to use this to solve problems like diseases? Because we have mutations. Mutations, mutations, if you're in biology or if you understand what that means, it's, we have some mutation like in sickle cell. It's simply because some nucleotides are maybe there is one amino acid that is missing here, or there's a mutation, there's this switch of this amino acid with another. Can we be able to solve that? Is it possible? Can we use computers to do that? That is what people are working on, to try to use this to solve problems, like to design drugs that will fix these kind of problems. Like you train this nucleotides. You are training the nucleotides. You are ensuring that it's able to solve, because we have billions of base pairs. Or like in biology, we have different billions of base pairs, and so it's too much for us to understand all that. Can we be able to train machines to be able to understand these billion pairs of nucleotides that we have? And it's able to understand that. And that's why we have the AlphaFold, and we have that's a 3D structure prediction, which they won the Nobel Prize, and also David Baker also won a Nobel Prize in trying to solve these kind of problems. So with this, we'll now talk a lot about the keys and all these values and all, but you can see it gone down to talk about every single thing. The attention score that I spoke about, how you calculate the attention scores, and you arrive at the most important part of your sentence. So this is all the calculations, and you can see it's giving me more things. And so with this, we can be able to, diseases, we have more than 19,000 diseases and less than 3,000 cures, or less than 4,000 cures. How can we be able to use this to solve those problems? So, and also in different fields, like in linguistics, we have computational linguistics, we have computational journalism, and in your own field, begin to imagine that we have pesticides that are not only killing plants, but those toxicants are now causing diseases. Can we now design better herbicides and better pesticides that are friendly to both the environment and humans? Those that are not toxic. Can we remove the toxicity? We can actually be able to design molecules that will cut down the toxicity level. So there's a lot that you can actually use this to accomplish. So having said that, if you follow, put a plus in the comment box. If you don't follow, put a minus. Let me check our understanding level, and then I'll move to the next. Once I finish those points, that'll be much easier for us to navigate on the slides and the examples I have. If you follow, you understand attention mechanism, put a plus. You understand so far to where we are, put a plus, right? It seems a couple of us understand that. So I'm going to go back to these slides, this notebook. And so this combo is what brought us to where we are today. And I'll be talking about machine learning. I'll be just talking about on my slide. I will show you how where it started and where we are. But I just wanted to understand this. Large language models are huge models with emergent abilities. So these are big models, huge models that has been trained on of data, billions of data, billions of parameters. So we'll talk more about that, but I want you to understand that ChatGPT, and you can see people sold ChatGPT and a lot of these big AI companies. I listed them, I think, down here. Um, I listed them down here, I think here. Where is it? Okay, you see OpenAI, ChatGPT. You see OpenAI. I think I had them somewhere. Okay, these are landmark papers. Okay, I have them somewhere. But maybe it's okay. Maybe it's all right. Maybe it's in my slides or somewhere else. But we have these models. We have this model that came out a couple of years ago. I just showed you Cloud, and you are familiar with all the AI tools. So I just wanted to highlight that these models have been built on so much data. And you see, companies or private firms are suing ChatGPT that they are scrubbing websites. You know, they are trying to maybe we go to our website, and then ChatGPT sort of like scrapped all the data here. They want to know everything that is on this website, everything that is on this our website. Maybe they scrapped it and they train, because the more you train, the more data you have, the more data you have. The state of AI we are is that the more data you have, the more your model understands better. But we're getting to an era where we're now talking about world models. Maybe you heard about that. World models is where we are heading to. We're heading to these world models where um, where it doesn't actually depend on so much data, but it can actually understand the world, it can understand the environment, and it can predict future events even without data. Where it predicts the future outcomes, where it's more intelligent than humans. So that's the spy intelligence we're talking about. And for some of you who follow the news and with what is happening in the AI space, this is the era. This is where we are moving. These world models. So this world models is where we are moving to. But the current state of AI, of where we are currently, we need data, millions of data. That's why companies, as you're using ChatGPT or Cloud, let me give an example. ChatGPT. As you're using ChatGPT, and probably you come to your settings, and this is an eye opener, because for some of you, ChatGPT is already using your personal data. If, for instance, you don't set it here on your security or your security settings, maybe you didn't turn something off. Enable device, okay. Or there is somewhere, not security, storage, data controls. There is somewhere where if you don't turn it off, ChatGPT is using your data to train their models. And somehow, you see, okay, well, that's not where it's been a while I checked this, because I don't use this that much anymore. But for those of you who use it, you know there's that thing where if you don't turn it off, it means ChatGPT is using your data to automatically um, train their models. You know, so because they need a lot of data, so the current era of state of AI is that we need data to be able to for for the AI to understand the world, because for now AI is depending on human data. AI is depending on us. It's depending on human data. So if you look at the large language models, you know, your models are able, your models, for instance, ChatGPT, sometimes it misses, it hallucinates. It doesn't give you, it forges, it gives you wrong references, wrong things. Why is it giving you wrong things? Like it hallucinates. Hallucination. So it tells you that, you see, look at what is written here. ChatGPT can make mistakes. ChatGPT can make mistakes. Check important info. So where we are is the state of AI. I mean, the current state of AI is not something that is 100% correct. We're in a state of AI where it depends on data. So if it doesn't have the data, if it doesn't train on so much data, it means it can make mistakes. It can hallucinate, and that's why they always say I can make mistakes. You go to Claude. I think I have it here. It's written here. Claude is an AI tool, and it can make mistakes. Double check responses. So it's still giving you the power to check that. Why? Because it's depending on humans. But let's go to our website, in the New Life Research Foundation's website, and go to About Us and learn something here, because we have AI here that we talked about here. We also mentioned AGI, Artificial General Intelligence. So we're moving to an era where we have AGI, where the systems are very powerful, that it can actually understand even on unseen tasks. And that's where even word models, and currently word models and JPA, we have these people who are training JPA models. For some of you who follow the JPA models, they are training those models to try to bring us to an era where we don't only depend on data, but just for the models can actually learn from the environment. They interact with the environment and they're able to learn, and they're able to, for instance, like a robot is able to do things even better, even without relying on what has been given it. So we have different papers that have been coming out. We have the word model which came out. This was the implementation of JPA. So this is where we are. We know that ChatGPT, I told you, you will go back to our slides again, or to where we were. I think we were here. I told you that the current state of AI is here, and we are building a lot of large language models and all that. But where we're heading to, this is where we're heading to, where we will not rely on data. But still, the model should be able to train and be more intelligent than we are. And so I implore you to, you can go to our website and try to read this as well. It's a good piece that we put it here. So I will go back to here, and then I will talk about the Gen AI, the generative AI, and we use this. ChatGPT is a generative AI. Why is it? Is because it's able to generate something for you. So it creates new content, text, images, and a lot of things. I can come to ChatGPT. You all upload things, images. I can upload something here. Maybe I have. Let me check if I have an image here. What type of image is this? Okay, I have this image. Can I ask? I'm uploading an image here. I can ask it, tell me what this means. I don't know the content, but I've uploaded something here. I know the Shapley values and all that. It's going to talk about Shapley values. You see, it's explainable AI. So this patient has 92% probability of Parkinson's disease. So he's able to explain everything in that image, and he's talking about that. So that is I've given it an image, and it's able to generate text for me. And you can give a text and ask it. I would say now design a flyer based on this. I would say design a colored square. I'm giving it specification square flyer based on this. So it's going to design, you see, I've given it text. Or maybe I don't have enough for here, for this. I should have enough, I think. Okay, it's already doing that, you see. So I asked you to design, I just showed you, I moved from image to text, and now I'm moving from text. This is a text I've given, and it's giving me an image. So this is generative AI. This is, you are giving an input. Your input can be text, it can be images, it can be other formats, and it's able to generate something for you, which is this. So you have an encoder, that's an input, and is able to decode, that's a decoder. We're going to talk about that subsequently, but that's the most important parts I want you to take note of: the encoder and the decoder. Encoder is the input. You are encoding. I mentioned it earlier that we encode our input. Our input can be text, it can be anything. And now you can see one last tweak is still working. Very soon it's going to finish. I believe all of us, we use this on a daily basis. You can see some of our flyers, some of the things that we've I think maybe I still have this on my, okay, I deleted it, but I just modified something on the flyer that we designed, and I did that using this. And I also showed you a couple of days ago that I prepared these slides using Claude. I showed you earlier. I just told Claude our color brand is deep blue and white, because those are our color brand based on our logo, New Life Research Foundation's logo. And you can see he prepared all the slides for me. Beautiful. So this, I gave the content, I gave it text, I gave it some info, and it's able to generate that. You can see this. So I gave it text, and it's able to generate something for me. And I can use this to explain everything on sharp line anchors. I can use this. Maybe I will even make a post about this after the class. You can see this on our social media. You may see this on our social media. So this is part of what we are talking about. You give it, I gave it, I will download it on my phone. But this is you give it a text, but it's able to generate an image for you. So this is generative AI. And how is this helpful? You can actually give a model some nucleotides. Let me go back to biology, because the most important thing to me is to be able to cure human diseases. So let me go back to that. I gave an example. I hope I still have that. Yes, I can give my model these nucleotides. And instead of, this is like, these are diseased proteins. Like, say these are diseased proteins, and I want to cure that particular diseased protein. I can actually design drugs that can target those specific sites, and then is able to bind to that receptor, and is able to cure the disease. But then I have to understand the protein. I also have to understand the drug molecule. What do I have to modify on the drug? What do I have to modify? The protein is there. I don't have to modify anything. I have to just understand the binding pocket. And then I now design a drug that fits perfectly into that target. And then is able to cure the disease. Because a lot of the drugs out there, they are not doing that. So I can actually give the constraint. The constraints are the conditions. The conditions you give. Okay, if it doesn't bind this way, okay, do it this way. Okay, understand the biology, and that's where the embeddings comes in. And we have like different models that have been trained on billions of of biological sequences, billions of DNA sequences, billions of RNA data. And so he's able to understand the biology language. So if I use that, and so if I just go to on the internet and I type something like DNA bath, these are DNA language models. So we have language models. This is a pre-trained bidirectional encoder representation. So this is to understand biology language. And what about RNA bath? We may also have RNA bath. You may also check your own field. We may have that as well. But you see RNA bath. This is to understand, this model is understand RNA language. The other one was understanding what? DNA language. You can have protein bath. Protein is understanding protein language. You can begin to check in your own field now. Let's see if you can get something. Protein bath. You see, we have protein bath here. What is this understanding? Protein language. Type in the comment box if you find something. Type in the comment box if you find something in your own field, like a model that understands the language. It could be anything. So, and you can go, one of the places you can easily check is on Hugging Face. And I encourage us to, each and every one of you, to go sign up an account. You can say have an account on Hugging Face. And on Hugging Face, I download some data. I have some language models I've used. I can show you some of the models I've used. Probably I may have some, may not have them there, but you can sign up on this and check, explore this space. Check. I can just type bath, and I will see a lot of bath models. Why is it not bringing that? Okay. You can see different bath models, I think, from here. It should give me bath models, I think, I believe. Or maybe I'm not searching it the right way, but you can actually do that. You can do that and check a lot of them. They've been trained in different feeds. We have image. What about image bath? Like for imaging, image bath. Oh, is it image bath or what? What do they call it? I've forgotten now. Let's see if we have image bath. You see, we have image bath. This is to understand images. To understand global images. That's all images around the world. And as you put your pictures on Facebook, Facebook is using your images to train their model. So it's understanding images better. It's able to recognize images. So what about med bath or maybe medical imaging? This we can check as many as possible and find them on Hugging Face. That said, I will go back to, because this is just an intro, I won't be spending too much time on that. But so you see, it says scale matters. Bigger models are smarter. Why is that? There is this struggle for more data, because your model learns from more data. As it learns from more data, it becomes more intelligent. And so that's why when you have a small data and you are building a model and you are using one of these models, these complex architectures like transformers, it doesn't do well. It doesn't do well. Why? Because you have a small data. In that case, you may decide to pre-train. We have pre-training. That's you pick. Let me give an example. I just mentioned that we have a model that has been trained on global images, all images around the world. Your pictures are also inclusive. It could be on Facebook. I can type. I can ask ChatGPT like Facebook's image model. image path is called. All right, I've forgotten the name. It's going to tell me the name of the Facebook, because they built the first image model. Yes, okay, this was Vision Transformer. I think this was a Vision Transformer model. Um, for images, originally introduced by Google. Okay, this was introduced by Google, but I believe there was also from, okay, image path. I think this VIT, this Vision Transformer, was from Google. Meta did did Dino or whatever. There's Sam. It's Sam that I actually wanted to talk about. Sam was trained. Sam was actually trained. Talk about Sam. Sam was trained on global images, and then, okay, it's saying I have one more message because I'm not using this. Sam is segment anything. Segment anything model. That's the full meaning. Segment anything. So as you can see on the street, if it's a dog, if it was trained on many images. So if you input something, it's able to recognize. But this was on global images. Then we had MedSam. MedSam. MedSam was trained on medical images. So be it in okay, MedSam, I will copy this and go back here. Where can I check new chat? Because I'm using free for this. So for MedSam, you see, MedSam was trained on medical images, and this was trained by Meta. It's the formerly Facebook. That's the brand. I mean, the company's name has been changed to Meta. So this understands all medical images. So when you see CT, MR, X-ray, ultrasound, pathology images, and all medical images. So when you now bring a domain-specific image, for instance, you have for CT in a particular hospital, because these are patients' data. So when you see this particular image from a particular hospital, you may have just a couple of patients, maybe 100 patients or 150 patients. So without 150 patients, it's not possible for you to train the model on these complex architectures that we have, like Vision Transformer. Vision Transformer is complex. It's a complex model. So instead of training this from scratch, you rely on a domain model. This is a domain-specific model. This is a medical. This is a medical SAM trained on medical images. These are medical images. So since it was trained on medical images, you can now use it for your own specific task. You don't need to go and train your own model from scratch. You just use this SAM, MedSAM, and fine-tune it on your small data, the 100 and something patients you have. And it's able to predict whether those patients, maybe they have a specific cancer or whatever you're going to predict, is able to predict well. And if you go to FDA and you check a lot of on FDA websites, you can see FDA approved. I would just say FDA approved AI diagnostic tools. And you see they are getting it into clinical trials. Or did I type FDA approved? So when you check this, you will see that the FDA, this is it. You will see that the FDA, because of the the ability of these large language models to understand medical images, we are able to we're able to design a lot of diagnostic tools. Which I was able to find the exact list. Okay, list of cleared. You see, list of cleared or approved diagnostic devices. And here you will see, if you go over this, you will see a lot of tools that came out from that medical SAM, because they understood the medical images. And then people began to now use specific data to really understand the the specific domain they were focusing on. I will not be going too much into that. I just wanted to drive to push you to understand that. I'm giving these practical examples to help you really understand what this is actually all about. And this course is not like the Python that we did in depth. This is an intro, so it's more like storytelling to really help you understand where we are and does this make sense? Can you go back and begin to look more into it? And maybe downstream, we can also have a more comprehensive course to talk about these things. So I just spoke about pre-training. You pre-train. Pre-training means you are training a model to understand a specific field, like medical image. I gave an example of medical images. You can train a model to understand global RNAs, and I showed you RNA bath. You can I showed you DNA bath, which understands global DNA sequences. So if I bring my own DNA sequence and I ask it to predict some SNPs, like single nucleotide polymorphisms, predict something, is able to predict some mutations, is able to predict some things. So he's able to understand that. And not only that, I showed you protein bath because I'm from biochemistry and all the bioinformatics in this area. I was just dragging it to my own field, but you can apply the same. You can look up on Hugging Face. You may find something in your own discipline because I've been in a class where we're asked to go pick up a large language model that has been trained to understand something that was not connected to my own discipline. And that can be linguistics, it can be journalism, I've been calling this, can also be law, it can be in different other field. So this is also applicable in your own field, in your own discipline. Going back to this, yes, so we on the very first day, I also mentioned that these technologies are changing rapidly. This this is a change that you can't really catch up with it if you don't stay in the loop. So you have to stay in the loop. And also, you can see I was doing some sort of like good, um, like um, like prompt engineering. Over time, we will focus more on prompt engineering. That's giving good prompts to the AI, or even down at the back end, people who are building these tools. But now we are seeing loop engineering is coming up, where it's a different paradigm shift. If you check our website, you see all this. Go to our Neural Research Foundation's website. I implore you to go to About and check on About Us. You will read more about this kind of things, where it talks about, we update this very often. If we see things new, we try to update this so you know where we are. So this talks a little bit more about where we started and where we are. It will give you a good understanding on all that. So I'll go back to where I was. I think I typed something in this ChatGPT, and I asked it, prompt engineering is a practice of designing inputs, that's prompts, to get better, more reliable outputs from a model like ChatGPT or other LLMs. That's large language models. All these are large language models because they are trained on big data, and even the models themselves, they are complex. The architectures are complex. They are not simple models like linear regression or logistic regression, which are just one line plot. But these ones are complex. They are complex models. So you see, it gave us that explanation of prompt engineering. It's giving us more examples of things like that. And I think it's going to now talk about loop engineering. It's about designing repeated cycles of reasoning. And that's where we are. So you see, we are moving away from prompt engineering and we're going to loop engineering, where these AI tools are designed to not only you give a prompt, the people at the back end have already designed a model, the large language model, to be able to repeat the task in terms of like, is able to receive feedback and reason, refine it, and give you a better output. So so instead of like a one shot prompting, like you just give like just a single prompt, and then it gives you an output. No, the model is not just giving you an output. The model is actually iterating to improve the output it gives you. It ensures that it gives you a good output. I give an example, and this is very recent. I remember I was trying to demo this in the morning. I just I couldn't get on the website. I don't know how it happened, but maybe internet connection. But you see, for those of you who visited our website recently, you will see that there was like no slideshow. But now we have slideshow. And this was done just yesterday. We updated this just yesterday. And this was done by AI agents, the co-pilots. And we just asked it to, there were some errors actually, and it looped and corrected all the errors. It looped and corrected reasons and it, you know, several iterations. It was able to come up. We didn't do anything. It just iterated and corrected every single thing that we needed to fix that. And then the same thing to a lot of sections that we updated here. We updated a lot of things on the website, and we keep doing that from time to time. So you see, that's part of the iteration we're talking about. So we are getting to an era where not only you, I mean, the engineers themselves, they are designing these tools to be able to, for instance, let me give an example. You look at even ChatGPT, when it came out in 2020, a couple of years ago, around 2022 or 2023 to I think 2022, it hallucinates a lot. But because of the prompt engineering, ChatGPT is also able to give you a lot of references that are correct. Because 2 3 years ago, you used ChatGPT, most of the references are wrong, or a whole lot of them they are wrong. But now the level of hallucination is down because the engineers are improving day by day to improve the output it gives you. So it runs, it evaluates, it improves, and it repeats it over and over, and is able to understand that. I ask you, I will leave it here, but I'll ask you to go. If it's something you're interested in and you want to keep learning, go learn more about this. This is just introduction, so we're just introducing you to these things so you know they exist and you can go and dig deeper about them. I'm going to push this to you, the slides to you, and also the notebook. I'll push them to you. But also, our website is there for you to also go and read more things on our website to about us to read, and you just keep checking the website. You keep seeing new things and a lot of things that are happening in the space of AI because we keep updating this from time to time. So, we having completed that, I'll now go back to my slides and then I will run over it in a couple of minutes, and then I will go back to the notebook, which is pretty straightforward. I won't be spending much time on that as well. Having covered these points, I wanted to just spend more time to talk about these points so you understand when we talk about NLP and all this, where are we? But I will just walk you through my slides. Where are my slides? Let me see. They should be somewhere here. Oh no. Okay, I think I have my slides here. All right. So in these slides, we are going to be looking at the definition of AI, ML, NLP, text, presentation and representation. All of this, you see, we've talked about all of this. So I won't be spending too much time on this, but I believe there are things you've already gotten understanding about just in a couple of minutes ago. So the AI, we spoke about that. It's designed to mimic human cognition, to mimic human cognitive functions. So when you look at, we are able to process information. As I'm talking, as I'm speaking, your brain is able to process information, what I'm talking about, and is able to translate it in a way that you understand. You're able to digest it. So artificial intelligence is nothing more than that. It's just mimicking human understanding, human cognitive functions. We know cognitive functions such as reasoning, learning, perceiving, and a lot of other things. Also interacting with the environment, which is where we are moving to. Interacting with an environment and is one of the things to be able to solve problems. Because there is a saying, I read a book, I'm still reading one of the books, which says that intelligence is not by, that intelligence is learned. Intelligence is learned. You are learning, you are in this summer school, you are learning, right now you are learning. So it's actually learned. So if intelligence is learned, it means if we can teach machines, if we can leave machines to learn, they can actually do better. And so the era of AI where we are moving is where we can we will not rely on data. Like, for instance, if I decide to condemn all of you in this class that you don't know anything, you are dull, you are this, you are that, it means I'm shutting your door. And that's why we made, for now we rely heavily on data, existing data. But even those data that we rely on, they are failing us because the models still hallucinate. It gives us wrong information. It means if I assess you now, I'll be wrong. I may assess you now that you are just a beginner in Python. You're just a beginner in this space. And for the next 5 years, you will still be the same, or you may not do well. I think I'm limiting you because you are able to learn. You learn by interacting with others, attending summer schools, practicing things, and doing a lot of things that we don't even know. You have your own way. You may even convert the whole of this into a song. You may convert it into a song, and that's the way you process information. That's the way you understand. That's the way you are able to solve problems. That's a key to your own intelligence. So we're getting to an era where we're beginning to understand that the models, they can interact with the environment and figure out things by themselves. Like self-driving cars, they can figure out things by themselves. So, for instance, we are training you here where we are just giving you the basics. This is part of the basics we are giving you, and then we leave you. And then whatever that happens is between you and your environment. How are you able to get all this and translate them into something that when we meet you in the next 4-5 years, you are an expert in your field? It's because the intelligence is learned. So there was this heavy argument between two, I think, psychologists. That one, I think, they're all from Europe. One was like intelligence is learned. The other one was intelligence is innate. Innate means you are born with it. But based on machines and based on how we learn from childhood to where we are now, the whole argument was going more. There was like more agreement on the fact that intelligence is learned. We have kids who are less than 15 years here. We have some who are less than 10 years old. But they are learning the same way. And also in this summer school, we have people who are 60 years old. And I want to shock you. We have over 60-year-old. We have 50 years plus, 40 years plus, 30. But we also have less than 10 years old. We have less than 20, less than 15. And they are all learning. If someone at 50 can learn something, can learn Python, and let me also shock you. The first two people who submitted the homework, the task we sent, they are less than 15 years old. They are less than 15 years old. We received them and we checked it, we were like, oh wow. This is like less than 15-year-old submitting the task before the 50 years old, the 60s, the 40s, the 30s, the 20s. So it means intelligence can be learned. These things can be learned. And so the machines can also be learned. They can learn things and figure out things by themselves, and that makes them intelligent. And so when you look at the kids who are less than 15 years, because of their interaction with us, and they've learned to figure out things by themselves, and they're able to solve the tasks. And so they are learning, their intelligence is increasing. They're learning to figure out things by themselves. And who knows whether one of these kids will build a game, because they love playing games. And because they've played a lot of games, they know the things they want and they know the things they don't like. They can they can bring up new games and even solve some problems. And so that's intelligence. So when you look at artificial intelligence, that's one of the things you should be looking more into. I'll leave the other content for you to go and look at them. And these applications, we spoke about it on the very first day, so I won't be going into these different sections, different aspects of artificial intelligence. But I spoke about machine learning, where from machine learning you have supervised and unsupervised learning. We'll talk more about that downstream, but also deep learning is also there. Natural language processing, we just spoke about that extensively. We have expert systems, speech recognition. Why is that when you use Siri, it's able to recognize your voice? We have voice recognition, and we have robotics. We have robots out there. We have planning. Like now that people are people are losing their jobs, jobs where in offices, like for instance, even in website development. I gave an example the other day that we were able to I was able to develop the website for my own company, and also for vibration for New Life Research Foundation. Just the updates that we made on the website is done by us. And so a lot of things are being done. People are losing jobs in terms of like planning and a lot of things. People use AI agents. I demoed it in the morning. You can put it on plan mode, and on plan mode, it plans a project for you. It executes. You put it on agent mode. The agent is able to iterate, and so the iteration, because there's also a human loop, and that's why humans are still very important, because there's a human loop in the system. So the human loop is to guide and to the critical thinking ability. I remember Bro Fred spoke about that on the very first day. The critical thinking is still very important, because you are still the driver of the whole AI agents. And so I've had situations where I trained, and if you watch the additional video, the additional recording we sent to you on how you can use Copilot, we're training our team, and in that training, if you watch the recordings, we were able to write a paper, we're able to download the data. The AI agents were the ones that went to those websites, downloaded the whole data, did the exploratory data analysis, trained the models, did the benchmarking, wrote a paper, and did everything in less than 3 hours. It was able to do all that. So that's where we are moving. That's where we are going. And in vision, I just spoke about imaging. I spoke extensively on imaging, and so you should be able to understand that. But also, Roland is going to take over from tomorrow, and he's going to talk more about machine learning and deep learning. So for deep learning and machine learning, unsupervised and supervised, he's going to talk more about that. So I will leave that for you to look into. So we have different sections which I just spoke about. All this these are things we've already talked about. I will send you the slides. I don't think you have the slides. I will send them to you. You have part of the slides, but not all the slides. But this is all the slides that you can go over and know that in machine learning we have different sections. We have different parts of machine learning where you can look into supervised, unsupervised, deep learning, and all that. There are classical machine learning that you can learn. These are classical machine learning you can learn. You can learn about neural networks, Ensemble, which random forest and all the XGBoost, all those models. And then we'll look into reinforcement learning and all that. Also, we have this explainable AI. I spoke about that extensively on the very first day. Go watch those recordings. I won't be going into these Shapley values and all this, so I can allow you to go look into the black box model. But your model is, you build your model, and your model gives a prediction, but the prediction is still a black box. The prediction is still a value. You don't know the contributors. And so I gave an example on this these factors. These factors contributes to Parkinson's disease and I think type 2 diabetes. And if you are female, it means you are favored. It means diabetes affects more men than females, because of waist circumference and a lot of things that affects men. Um, so we looked into this the very first day, and we looked at different um, 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 contributors to that. I mean, how much we quantified how much it contributed to the model, and we did all that. So you can go look more into that. But that's it. We also looked into reinforcement learning, which is the reward system, and I won't be going into that. Where if it does well, you reward it, and then um, and that's is deeply applied in robotics, because of the self-driving car and all the robots in different companies and different industries and all that. We won't be going much into this, but if you watch the first recordings, you should be able to understand this better, which I spend more time on that, and also last year's recordings are also there for you. But these are parts of what we are talking about. And so this is nothing new. It's what I've spoken about, which I mentioned that this is based on linguistics. So those from linguistics know that natural language processing, which is a computer term, was gotten from linguistics. Artificial intelligence was gotten from neuroscience. So those from neuroscience know artificial intelligence was gotten from neuroscience. But when we talk about natural language processing, it was gotten from linguistics. So it's a way of combining linguistics, computer science, and AI to really understand humans and machines. That's the communication between humans and machines. And so we are able to also solve problems like even designing drugs for different human diseases. I spoke extensively about that, and this is like the timeline you see. We had back in the 1950s. It was a rule-based system. We didn't have a lot of advancements in AI because there were a lot of people that were against AI, and it was only in the 1980s that we had deep learning. And I don't have all the time. I think I have some of the timelines here. All of them may not be here, but it was only in the 1980s that we had deep learning, and then it began to, because even at that, when Yann LeCun, when he built some systems that were being used by banks and different companies, people still didn't believe it, and he had to even leave France to Canada, where he lived and worked in the lab as a postdoc, and then he worked with his PI in Canada, and while working with him, they were able to move the field forward. The deep learning came to the mainstream, and by 2012 we had AlexNet, and then down the line we had in the 2020s, you see 2010s to 2020s, that was when we had AlexNet, and then we had 2017, attention is everything we need, and then NLP was there. And then today, by 2022, down we have all the ChatGPT, and the whole technologies are changing day by day, and now we have agentic AI, and we have loop engineering, and a lot of things are changing so fast. So and then you process your text. You preprocess your text. I have to spend a little bit more time on this. So so you feed this text into the model. It doesn't actually understand text, just like I said earlier, but um, there is text processing where it's able to split this, because these are two words. These are just two words, like these words, and these words are just the dog. And then here you have hello world is also two words. You have this is a pen. Um, Here you remove the common filler words, which is this is a this the main character here. That's the attention here is on pen, and all these other ones you drop them. The punctuation remover here, you remove this punctuation. They are nothing difficult here. Lowercasing here, you just drop the capital letters, and then you drop it from uppercase to lowercase. And here, that's the text processing. There is nothing difficult here. Here you reduce the words to base root, from running to just run, because the run is a base root. And so this is just about text processing. We won't be going too deep into this, but we have different types of word representation. I'll leave you to look into that. But we also have tokenization, and I think I should talk a little bit about world. We have word embeddings. We have sentence, because you can convert sentences. Sentences, you have words. Sentences, you have words. Um, you have words. You have sentences that you can actually convert them to words. Or you can convert them to actually vectors. That's numbers, because that's the language our computer understands. And that brings us to tokenization. So tokenization is a way of just splitting words, or it could be text, it could be words, it could be sentences. So you have text, you have words, you have sentences. You split them into chunk. You chunk it into smaller units. And we have also different types of tokenization. We may not be able to go deep into that, but we have different types of tokenization. We have character tokenization. We have different types of tokenization. We have byte pair encoding. We have different parts of that as well. So we won't be going too deep, but I just want you to also understand. And also, I did this deeply last year. I've already talked about this even in the other slides. But I also want you to understand that to tokenize a sentence, this is a sentence: I went to New York to play football. Each of these is an individual word. This is a sentence. So for you to tokenize this sentence, you break this sentence into chunks, into individual words. And so if I want to count the number of tokens I have here, so each of those words represents a token. So you split a sentence and it represents, each word stands for a sentence. It stands for a token. So if I split this sentence, I went to New York to play football. I've split this into their individual words. I went to New York to play football. So how many tokens do I have here? Type in the comment box. I went to New York to play football. How many tokens do I have here? It's a process of splitting text object into smaller units. And I said earlier that you can split words, numbers, symbols, engrams, and characters, sentences into smaller words. Let me see the answers you have. How many tokens? 7. Okay, 7 tokens. 7 tokens. And the other person that said 6 tokens, let me see. Let's count them together to see if we have 6 tokens or 5. Where are my slides? Okay, I lost them. But let's go back here. Where was I? All right. So I was here, and let's count them. 1, 2, 3, 4, 5, 6, 7. So these are 7. You don't undermine it, even if it's a full stop, it represents a word. So if I had like say an exclamation mark at the end of this football, exclamation mark is going to stand on its own. If it was a full stop, it's going to stand on its own. If it was something like a question mark, it was going to stand on its own. The question mark is not going to be part of football. The question mark stands as its own token. And so let's try this as well. So we have football, cricket, golf, tennis. So if we split this, we are going to have football as a token, cricket as a token, golf as a token, tennis as a token. And so in this case, how many tokens? And then, but remember, also we have remember we have this. So how many tokens do we have here? How many tokens do we have here? All right, 4. 4. Okay, someone is saying 4. But also, do you also know that the when we go, if we uh, now you see there's an issue. There's an issue. If we go back here and we count the number of words we have here, we have 7. We can easily say we have 7 tokens. But I wouldn't agree that we have 7 tokens. And I wouldn't agree that we have 4 tokens. Because in this sentence, we have these quotes. You can see these quotes. To me, these quotes are part of the sentence. These quotes are part of the sentence. So if I were to count the number of tokens in this sentence, I will have 9 tokens. And if I were to count the number of tokens I have here, because I have all these commas, all this, I have a comma here, I have a semicolon here, I have all this. So my tokens are going to be 1, 2, 3, 4, 5, 6, 7, 8. 8 tokens. 8 tokens. So now the computer doesn't understand all these exclamation marks, all this noise. I will call it noise. They constitute noise to your data. So feeding this into the model or trying to tokenize, because you are breaking it into smaller pieces, you will lose some signal from your real data. This is your real data: football, cricket, golf, tennis. If I leave all this, it means I'm leaving some noise in my data. So basically what we do is, and this is also applicable in biology, for those of you in biology, you know we have 5' to 3'. We start from 5' to 3'. That's where the first sequence starts, and then we have 3' to 5'. So that's a reverse strand. The forward strand, 5' to 3', and the other strand is 3' to 5'. So if you are feeding standard nucleotides into the model to learn DNA language or to learn RNA language, those 3', 5', they are going to constitute noise to your data. So basically what we do is we strip this, all this noise, we strip them. We strip all this constituting noise in our data. We strip them before tokenizing. So before tokenizing anything, and also your projects, you're going to get, after today, we are going to give you a task. And in that task, we ask you to, some of the tasks you're required to strip this and count the number of tokens. So you strip, like here we have these codes. So without the first step in text processing is to strip this noise, and then you'll be left with only these tokens. If I strip all this, I will have only 4 tokens. But if I don't strip this, I will have multiple tokens. And those tokens, do they have any relevant information? Now let me ask, does this codes, does it tell me, give me any information about the sentence? It doesn't. And so it is to people who are doing biology, because those 5' to 3', they may give you the biological information that, okay, this is the forward strand, this is the reverse strand. But also, you don't understand, it does give you that. But in a model, you are not modeling forward and backward strand. You are modeling sequences, standard sequences, to cure a disease. The forward and the backward strand won't cure a disease. It is the standard nucleotides that you modify, that you work on, that you do all that is going to sort of like give you the answers to your questions. So it's always good to strip all this before counting the. If you are asked, if you are asked about the, if for instance you are asked about the number of tokens here, these are the tokens. So you will count every single thing here, and it's going to be a lot. But then after text processing, after you pre-process it, you now strip everything and you're left with very few things. So we are trying to, okay, let's do, we have some types of tokenization. We have world level. That's the world level. You have, we have an example here. NLP is fun. And world level, you tokenize by the number of words you have in this sentence. This is a sentence. So it's world level. And so NLP is going to stand on its own. Ease is going to stand on its own. Fun is going to stand on its own. So this is world level. This is world level. So if I ask you how many tokens do I have here based on this world level, it's going to be 3. 1, 2, 3. Then we have sub-world level tokenization. That's what we call byte pair encoding. I mentioned it earlier. BPE, byte pair encoding. We have an example here where you tokenize sub-word. This is a word on happiness. And unhappiness is a word. And we have, and that's why it's English, and we are learning English now. We've gone back to English. And so you have syllables. In English, you have what we call syllables. So you have to split this based on syllables. On happiness. So we have 3 syllables in this sentence. On happiness. We have unhappiness. So this constitutes the number of tokens we have in this world. In this world, we have unhappiness, and this is what we call sub-word tokenization. Sub-word level. Sub-word level. Sub-word level. For instance, in biology, I'm always giving those examples. You have DNA, and the DNA, they are made up of not only nucleotides. Nucleotides, they have bases. They have bases. They have, you have the sugar moiety. You have different other things that you begin to look into, different things. So here you have like the unhappiness. You have only 3 syllables, and this gives you only 3 tokens. So outside that, we also have, okay, an example. We have sentence level. So you have to understand these are very easy. These are English things. These are things that are not difficult. So we have NLP is fun. NLP is fun. It powers chatbots. This is a sentence. This is a sentence. So we have NLP is fun. So how many, if I ask you how many tokens do we have in this sentence? NLP is fun. It powers chatbots. How many tokens do we have here in this sentence? Remember, it's not sub-word level. It's not word level. It's sentence level tokenization. So how many do we have? Let me quickly look at the comment box and see your answers. How many do we have? 2, 2, 6, 6, 2. All right, I'll go with 2 because if you go back to the slides again, let me go back to the slides. I think I lost my slides. Whenever I leave, I have to come back. All right, so let's count them. NLP is fun. It's a complete sentence because there's we have this full stop, and this full stop shows that the sentence ended here. But because it's under quotes, look at it. It's under quotes. It means it's still a sentence. So we have 2 parts of the sentence. NLP is fun. It powers chatbots. We have two tokens here, this part and this part. So there are only 2 tokens in this whole sentence. And we have some other things here. Tiger is similar to lion. Mathematics is similar to statistics. Well, these are words, embeddings. And in this case, you are focusing on the most important parts of the sentence. And the word I told you in this word, tokenization, you are ignoring is similar, and also ignoring this too. You're focusing only on statistics, on this mathematics and statistics. These are the key words here. And if we are going to um, calculate the attention scores, that's the attention mechanism that I spoke about. You will calculate the attention for mathematics, attention scores for mathematics is similar to statistics. But in the end, you will have mathematics and statistics as the main focus. Likewise, tiger and lion. These other ones are filler words and they don't mean anything. So, having said that, we have more things about that. You can go over them. They are not so. There are more examples that you will learn more about text classification. They are not anything new. It's just applications of how these things are applied in real life. Um, and so I spoke about all this. I've walked you through some of these models. The encoder and the decoder. The encoder is the input. The decoder is the output. I've already walked you through this, and I showed you some of the frontier models out there. That the bad models they are domain specific models. I showed you the protein language. It understands protein language, so it has been trained on millions or billions of protein sequences. All global proteins were trained so that that model understands protein language to help us to find cure for diseases. If it's DNA, it has been trained on all DNA sequences around the world. It may exclude some sequences and that's why there's bias, and somehow some sequences may not be there in some parts of the world. But the whole idea is that we all come together and ensure that the DNA language models, as we say, they are all inclusive. They don't exclude other population groups. Like if the bat was trained in the United States or in the West, it should encompass data from Asian countries and also from Africa, from different South America, from other parts of the world, and so that makes it more inclusive. So we have different of such models. I won't be going into that. I've already talked about pre-trained models, and I've already talked about this as well. This is the attention mechanism. So the attention mechanism works such that you have an input, and your input is converted into embedding. This is the language. We talked about the embedding. That's the language that this understands. Understands. And remember, you strip all the positions. That's you see you have in DNA you have 3' to 5'. So when you are creating embeddings or tokenizing, creating embeddings and tokenizing, they go hand in hand, because the tokenizing is embedding. It gives you a vector, it gives you numbers, because you want to have a numerical format. You want to have a format to feed into the model. And the same thing with tokenization. You tokenize, but you don't end up with just those words. As we're tokenizing, we're counting those number of words. You can't feed that into the model. You must assign numeric values. If I say I love oranges, I may say I should stand for 0, love should be 1, oranges should be 2. So I have 3 tokens, 0, 1, 2. 0, 1, 2 are my tokens. My tokens are not I love oranges. I love oranges is a text, and my model will not accept that. That's not a good input. The input must be numerical. And that's where you input here, and you can learn the inputs. Sometimes you can learn it from richer models, like other pre-trained models that are out there. I won't be going too deep because it's an introductory session, so I won't be going into how do you create embeddings from other rich models out there. I won't be going into that, but you can actually create rich embeddings from existing models out there. Foundation models, we have foundation models, and foundation models are big models out there that has been trained on massive data. So I won't be going into that, but we have that. So this is your encoder and this is your decoder. I mentioned earlier that the encoder is receiving your data. Decoder is outputs, is giving out something. Encoder and decoder. So we have the decoder part down here. And so here you remember you strip all all the noise, um, all the codes, all the number, all the things that will constitute noise to your data, all the things that are not your real data, you strip them. So after you do that, before training your model, you add positional encoding. The positional encoding is to ensure that your model has the positions. Like now you are bringing back you are ensuring that it understands the positions. Like if it's 5 prime to 3 prime, it understands this is the arrangement. It's 5 prime to 3 prime. If it's DNA, it understands that this is DNA. If it's the RNA, it understands it's RNA type. That's the nucleotide type. And so you're able to do that and walk over the architecture. You have the multi-head attention. We spoke about the attention mechanism. You cross-attend. You cross-attend on all your inputs, and then you normalize. You feed forward. As the feed forward section. You remember in deep learning, we're going to talk about that. Ron is going to talk about that. But we have the feed forward, and then you normalize again, and then it goes into your decoder. So you can actually mask. You can mask if it's something, you can mask. I mentioned about masking. You can actually mask um, sections of your data. If for instance you are predicting, you want to predict, um, you want to see if your model predicts the next token. You can actually mask some tokens that are real. In your input, you mask some tokens and see if it's able to still predict without missing those original tokens. So you feed a mask input. The input is masked. It's not having the complete information, but your model is able to predict the correct information, and that's what ChatGPT and all these AI tools have done. So it's a section of the input is missing, but the model is trained to be able to predict that. And then you follow all the other steps, and then the soft marks, and you have the output. We have different Gen AI models. I've spoken about the generative AI. I've given you examples on ChatGPT and all that. We have different models. I've been talking about transformers. It transforms from one language to another. It's able to decode information. We have the encoder side and the decoder side as well. Likewise, the autoencoders and diffusion models. We have all that. They all have the encoder and the decoder. So those are examples of Gen AI models. We also have generative adversarial networks. We have now even have diffusion language model. We have diffusion language model. It's another one that came up. And then the prediction of the next world is what we call auto-regressive models. So it's able to predict the next world after you mask it. You mask some sections of your input, but it's able to predict the next token. So that's the autoregressive, and we have different other models. We know about T5 and different other models. This is just a more explanation on them, whether they have an encoder or they have a decoder. This is just all about that. You can know. I just mentioned that in the last slide, that most of them they have an encoder and they have a decoder as well. But like you can see, GANs they don't have an encoder. It's just a decoder that they have. And yeah, we won't be going much details, but this is an encoder and a decoder sections where you have this encoder. This is you are inputting pixels, image pixels. These are pixels of images. You are inputting them into your data, into your model, and what it's doing is reducing the dimensions, reducing the dimensions of your data, and getting very high resolution images. That is bringing it to this latent space. This is the latent space. The latent representation is the high resolutions of your input. It has compressed it to. It's just like you can liken it uh, to feature selection. You select, you reduce your dimensions. You reduce your dimension to the most promising ones, and from here you can reconstruct those ones to something new. These are not the originals. The reconstructed ones are not the originals. So we have this is the decoder. The decoder reconstructs your latent space. This is your um, this is your input, this is your Z space. Your Z space is your latent space, which is your compressed or um, your reduced dimensions, which you're able to reconstruct to have something new. I give an example. You have a drug molecule here, it's a naturally occurring drug. It's a plant. Let's say it's a plant, and it's not diverse. And that particular drug is promising maybe for liver cancer, for cancer of the liver. But because it has some toxins, it has some things that needs to be removed, you want to design a molecule that doesn't have those things. So you can actually use those molecules and define some functions. You see these sections. You are defining some important things that should be done on that drug. And you can have those constraints. You can define those constraints at the encoder and also at the decoder. You may decide to define those constraints only at the decoder. Your constraints could be that this drug is promising. This is a medicinal plant, but it's a naturally occurring. It's not diverse. I want to have a synthetic drug that is more fitting, that is not toxic, that you will sort of like maybe the size was also big. Can you design something smaller? Maybe this drug was to cross the blood-brain barrier, maybe to go and cure or something like Alzheimer's or something like opioid addiction or something like Parkinson's disease or any of the neurological diseases. So how do you now define those functions? How do you now give those constraints to the model? So your model understands that I don't only have to bind, I have some other constraints, I have some other things that I need to understand. I have to be able to cross the blood-brain barrier. I have to be able to be administered orally, not only by injection. I have to be able to withstand the water medium in the body, lipophilic, and different other physicochemical properties. And then you define all the constraints. Not all, but you give the most important constraints. And also I mentioned motif as well. Motif is also a very good conditioning. It's a very good conditioning factor that you can condition. And then, but downstream, you can also conditions for some down here, for some here. And then even after you reconstruct, you can still go downstream and do some other analysis, like in this space we do molecular docking and all that to also see. And then also in the wet lab, you can also validate them using all those approaches. So this is a clear example on how autoencoders is applied. But you have also foundation models, which I mentioned earlier. They are large models that have been trained on broad data. I mentioned that earlier. And then you use them on downstream tasks. I gave an example on SAM. SAM was trained on large images. All images, Facebook, Strap, all your images, all your images that all your photos that you uploaded on Facebook, probably. So they trained that SAM. SAM is a global image model. And then the SAM doesn't really understand, doesn't do well on medical. If you use like you bring some data sets from like from your CT scan, the SAM failed because SAM was trained on people's pictures, images. It was trained on dogs, so it doesn't understand the medical images. Medical images are dark, they are different. Their pattern is different, everything is different. So it wasn't able to understand that. And then people say, okay, let's train a model that understands only medical images. And then they train medical SAM. Medical SAM is a clear example of a foundation model. And then people can now use a medical SAM, just like I gave like the example on downstream tasks, like CT. It can only be CT. People with CT, and they have a small data they can just run to. It's just like a child running to their dad or to their mom when they feel hungry, because they cannot cook. A child of 5 years can't cook. A child of 3 years or 2 years cannot cook. So they have to run to their mom or their dad, and this is their dad, because their dad has had a lot of experiences. Those experiences are the training it has gone through. It has been trained on so much data. The mom and the dad has been trained on so many life experiences, such that they can be able to understand what the child needs. If the child can't speak, the mom will understand this child needs some food. Or the dad sometimes the dads also understand, but sometimes the dad may not be so good at understanding. And that's why some models are not also so good, and some are better than others, and that's it. So, but we have those foundation models out there, and there are very many. I mentioned some to you, DNA bath and RNA bath, and a lot of other models out there. And I gave you a task: go on Hugging Face and go and look for. And maybe we also give you a task. One of the tasks we can even give you: go on Hugging Face and search for foundation models in your own discipline. And let's see how you can find them. You can find application in your own field, because you have a low data. You have low data situation where your own data in your own field is small. You need something to rely on. So you are training on something bigger. By so doing, you are able to um, make meaning out of your small data. You're able to still make meaning out of it. And it saves a lot of computing power because you're not training from scratch. It has been trained before, so you're only using some layers. It could be the last layers of the training, and then you use the last layers of the training and you fine tune on your small data, and that brings a lot of impact on the field. So, and then we also have different applications. We have different applications. I mean, ways of testing the accuracy of this. I'm going to skip all some of these ones, but the main ones. The main ones we have are Perplexity, FID score, front-end, and then we have Blue Score as well. Blue Score is there. Those are the key ones that we have in this space. So when you talk about uh, models to predict, metrics to measure whether these foundation models were able to do the task they were asked to do, is if it's predicting the next world, how well did it predict the next token? How well did it predict the next word, or the next thing that you wanted to predict? And so we have different metrics. You can read more about that. But we have Perplexity, which is one of the key ones that people use. We have FID and Blue Score. Those I'm just mentioning. And then also ROG Score. These ones are basic scores that we all know. You can still measure these ones. They are for classification tasks. But for language models in particular, Perplexity and FID Score are the main ones that people use. For translation tasks, Blue and ROG scores are the main ones. And for these metrics, each of them have their own definitions. And for instance, Perplexity, the lower the better. If you have a smaller Perplexity, it means your model actually did perform well. It did well on the task you wanted it to predict. It also depends on the number of tokens you have. If you have like 4 tokens, it means your Perplexity should be your max Perplexity should be 4. That's the max. So that means you are looking at your Perplexity reducing. So something like, I'm using 4 because of the 4 nucleotides in like DNA. Your Perplexity, if it's the lower the better. If it's 1 point something, then it's good. A perfect Perplexity is also not good. That means your model predicted 100%. So if I see that your model predicted 100%, I will run away, because most times the model is overfitting. Overfitting means, and he's going to talk about, Ron is going to talk about that tomorrow. Your model learns too much from your data. It memorized, and it didn't actually perform well on that task. So Perplexity, the lower the better. If I have a Perplexity of 3.5 and 2.5, I'll go for 2.5 because 2.5 is better. If I have 1.5 and 2.5, I'll go for 2.5. I'll go for 1.5, I mean to say, because 1.5 is a lower Perplexity. And the same thing applies to not each of these definitions. I'm just speaking Perplexity because it's the most important metric in language models. And we have the FID score that people use as well. You can look that up and check their meanings. What do they mean, and get to know more about that. So the Perplexity measures the uncertainty. The lower is better. I've talked about that. Okay, so I'm going to pause here, and I'll check your understanding level. I know it's a high level something. That's why I didn't want to, I was not looking at going this deep. But somehow when you are doing this, you don't know when you go too deep or too shallow. So I just wanted to ensure that you still understand, because I do know I'm going too deep beyond your level of comprehension. If you still understand, put a plus. If you don't understand, put a minus. Let me see your level of understanding. You still understand, put a plus. You don't understand, put a minus. All right, it seems you still understand. You still understand that. Okay, so I'm just trying to round up now. Um, so to round up my talk, I will be going back to my slides. And over my slides, these are just applications of just the recent trends in NLP. Um, you will go through them, zero shot, one shot, and all those terms. This is to help you to understand. I just spoke about responsible use of NLP, bias, and all that. They are prone to happen. I spoke about multimodal NLP, where you train on different types of data. It could be you bring both images, audio, video. You train everything together. And in biology, for instance, when you talk about multimodal NLP, you are talking about not just the DNA. The DNA stores information, but you're also looking at their expression level, and that's where the RNA-seq data comes in, where you're looking at how does these genes get expressed. And you're not just talking about that, you also look at clinical data, because the fact that genetics loads the gun is like human diseases are caused by genetics, but your lifestyle matters. Genetics can contribute 40%, but 60% can be from your lifestyle. Maybe someone who smokes or drinks is prone to having something like type 2 diabetes, you know. So environmental factors, or someone um, who eats terribly, who doesn't eat healthy, he eats just anything, they are going to have poor health outcomes. So all those data, they contribute to you actually trying to find the cause of a particular disease. It's not only the genetics, you're also looking at the person's gene expression. And the gene expression, I give an example. Two twins can be born, twins, twins can be born in the same environment, but they can have different health outcomes. One can be eating healthy, one can be living, one may not be eating healthy, may be living a different lifestyle. And based on the health outcomes, one may have diabetes, one may not have. So that means their genes are expressing differently, even though they're in the same environment. But because of what they eat, their lifestyle, their genes are expressing differently. One, the genes are expressing in a negative way, that's try to trigger diabetes. The other, um, the genes are not trying to trigger diabetes, type 2 diabetes. So that's part of the gene expression level. And you may also look at some other factors that can contribute to that. I just gave an example on that. And yeah, so I spoke about prompt engineering. I don't have to go to that again. I spoke about large language models and foundation models. We have different large language models out there. Instruction tuning. I spoke about fine tuning models. And we have a lot of data out there as well. Check Hugging Face. Ensure that you sign up an account on Hugging Face. And then the application is always, because the biggest thing is, yes, I love your field. I wanted to build things, build bridges, build everything, but healthcare. Your health is very important. So it's this. We have a good application of this thing in healthcare, in finance, in customer service, in education, in legal tech. We have all this in all disciplines. Go look it up in your own field. Go on Hugging Face and check how these things are being applied in your own field. So with that, for the slides, that's it. And then I will quickly move to the notebook, which I'm not going to be talking too deep, and then I will send it across to you to go look it up. But here is my notebook. I believe it's this here. Okay, so I have this notebook I prepared. This is just for beginners, and there is actually nothing new. This is just about the definition of AI, what is AI, and the application on daily basis. You can go over this, and then here is just machine learning. What is machine learning? So machine learning learns from data. Before, we used to do this manually. Like, you spend millions of you spend so many hours trying to figure out, like, you have a spam in your email, and you are trying to figure out, is this a scam or is not a scam, in your spam folder. can you push this to the spam folder? You know, you have a lot of emails that you can manually push them to the spam folder. But have you asked why some messages go, you go to your email and you go to your spam folder and you discover that some messages are directed to spam folder because they've been detected as scam. Even on messaging on SMS, we have that as well. Like here in the US, we have a lot of scam calls, scam text, you know. So why do they do that? Because they are using AI. The AI is classifying. This is machine learning. The AI has learned from words, that's learned from the data to know when something is scam or not. Instead of manually checking like whether this contains this contains this, it has learned from all that. So it's able to, once the message is like free money today, if it's spam, it's going to send it to spam. If it's meeting at 3 p.m., it knows that there is no, you know, see, if you look, you compare this and this is relying on free money, but is also relying on so many things. But here, it's able to select, classify both, you know, the good and the bad. Like if you have a meeting at 3 p.m., it's not going to send it to spam. But if it's free money, it's going to send it to spam. If it's click for price, it's spam. It's going to send it to spam. Project updates attached, not spam. So this is classification. It's a classification task. It's either 1 or minus. It is either 1 or 0. 1 means it's good. 0 means it's bad. 1 is like either this patient has a disease or this patient doesn't have a disease. So what we've done here to print this is just to show you that with machine learning, you can be able to detect spam emails instead of like writing the rules like manually and things like that, because it can misclassify like something. You can see congratulations. If it contains congratulations, you can send it to spam. Meanwhile, this is not part of spam. It may be something from your school. They're congratulating you that you won a scholarship. But then it sends it to spam, and then you miss that opportunity. You know? So machine learning has been helpful in trying to help us in doing that. And also, I gave more examples here. There are things you can see from the slides as well. And this section is talking about the types of learning, the supervised and unsupervised learning. Supervised learning learns from the target. You have, is either this, you have, if you have like healthy, let me give an example in the medical space, you have like healthy patients and unhealthy patients. That you have those with the disease and the controls. Controls are those without a disease, and the ones with the disease is what we can call like the ones with the disease, we can call them as 1. The ones without the disease, we can say is 0. So with that, you can also be able to, that's the target. The target is whether this patient has a disease or doesn't have a disease. So they have a label. There's a label. They have a disease. The label is what? Disease. The label is whether they have a disease or they don't have a disease. It's one of it. Either it's spam or not spam. But then also you have unsupervised. And the unsupervised is, it doesn't have any label. You have this massive data. Different ages, people with different ages, with different spending, this thing, different visits, visit 20 times, that's for this customer, visit this 20 times, or to maybe probably is a customer grouping something. So, but with this, you can be able to, maybe you are operating a shop, you can be able to know who, with this large data, you can be able to know who, which of your customers is going to churn, that's which ones are going to stop buying from you, and which ones are going to be your repeat customers. So with this is something you can see here. It does group like young people, high spenders, frequent visitors. They are going to definitely be people. But you see, is there a plus or minus? No, there's no label. All customers, they come to your shop, they buy things in your shop. All you are doing, you don't know who is who. So there is nothing like healthy patients or healthy patients. You collect all this data and then you train to know from this pattern. This is a pattern. You are learning from a pattern. So this is a pattern that you are learning from. And when Roland picks up tomorrow, he will talk him more deeply about unsupervised learning, and also how deep learning helps us to also do this. So this is learning from a pattern. A pattern is because this person is young. You're learning from a pattern because these are young people, and you know they can spend. You are learning from high spenders, like people who spend a lot. You're learning from that behavior. You're learning from that pattern. And this is also frequent spenders, frequent visitors. These are people who visit frequently. And these are people that you are expecting that they are going to be spending more. So this is just learning from this pattern. And then you're also learning from another group. And these ones are people who are not going to be spending more, older people. They are more careful in spending. And also low spenders, people who live on a budget, they are not going to spend more. Rare visitors, people who don't visit, people who maybe just buy something like once in a while. They may just go for shopping for just once in a month. Some people go for shopping once in a month. So with this, you'll be able to know how you channel your energy. You channel your even customer satisfaction. You want to retain all customers, but you are able to, if there are services or there are incentives that you want to give, you're going to focus more on this. But this is unsupervised learning. So it has no labels. And then we have also, I gave an example on reinforcement learning. In a reinforcement learning, you have trial and error. It's just a trial and error method where I give an example, like you have a robot. You are teaching a robot to walk. And if a robot walks, you give it a trial. That's just a trial. If a robot tries to move their left leg and then it falls, if the robot tries to move their left leg and it falls, it means it's -10. It means you are not going to reward the robot. It's just like your child. You have a child who is a high spender. You give the child money probably to spend, and that child spends that money in a whole day. It means you are not going to give the child any money anymore for that day. So this means no reward. Let's look at the second one. Now the robot tries to move their right leg first and then left. The result is it moves forward because it has moved the left, the left, and it moves the right leg, and also it moves the left. It means progress has been made, even though not the expected progress. If you give your child some money and your child spends it, it doesn't spend it in a whole day, but maybe he spends it just in a week and then comes back, at least you are going to reward the child, not much, but maybe you will give the child maybe $5. Here you are rewarding, but not so high. You're rewarding little. You are giving a test. Let's see what the child does. Let's see what the robot does. And then the next step. This is the next leg. This is the next step. Then the robot adjusts balance while moving. That's the next step. That's the next. So now the robot is learning. The robot is learning how to walk. Now to walk, I need to balance. I need to have a balance. And then once they have the balance, it's just like your child now learning that, now to spend, I need to live on a budget. Because if I don't live on a budget, I'm going to spend all my money within 1 week. And your child now lives on a budget, not so much, but knows that to live on a budget, I have to have a budget. But the child just knows that this budget exists, and budget exists. So I'm going to but they don't write it down. They know a budget exists. They just have it in their head, and then they go with the money, and then they end up spending the money for 2 weeks. It's progress. If the child comes back, you're going to reward the child with more money because they are making some progress. And you can reward the robot with some more points, 20 points. And then you keep iterating that. And then until you reach the optimal working strategy. Until your child reaches a stage where they can be able to write down their budget and live on a budget. They don't buy things. If your child can go within or several days without buying anything, or even if they buy something, it's just very few. Maybe in a week they buy something with just maybe $10 or maybe with $20. It means they've learned until they reach the optima, and then that's the step you're going to use. If you have any questions, put in the comment box. If you understand reinforcement learning, or if you understand supervised learning, unsupervised learning, or you understand all from this notebook, put a plus in the comment box. If you don't understand, put a minus, and I will know about that. So I just spoke about robotics. Robotics is very important, and I think someone also commented one of the and also in this reinforcement learning, you also optimize because you optimize. This is you have reinforcement. You're moving from supervised, unsupervised to reinforcement, because you also when it comes to even modeling, where you have pre-training, you pre-train a model. That's the first step. The second step, you fine-tune. The next step is reinforcement learning. So the reinforcement learning is to reward. That's to optimize. You're optimizing your model to do things better. Okay, I've trained my model. Okay, I have a foundation model, which is a pre-trained model. And then the pre-trained model was trained on like medical images. That's good. I fine-tune it on maybe CT scan. That's good. But the next step is I can do reinforcement learning. The reinforcement learning part will come to optimizing, sort of like trying to see if the CT scans can generate even better images. That's better predictions. In this case, because the whole idea is to predict, is to diagnose a patient, is to diagnose a disease. So from there, if from your reinforcement learning, because we have you can use your reinforcement learning to optimize. You're optimizing the ability of your model. That's your fine-tuned model, to generate something better. If it's something like DNA or RNAs, or you're designing a drug, can it actually do something? Can it actually optimize? You can use it. Some of you are aware of Bayesian optimization. So you can liken reinforcement learning as it's an architecture of its own. You can train a model from scratch with it, but also it's more or less an optimization when it comes to all this AI, because that's where people are going, and I'm showing you where the world is going, where people are using reinforcement learning as an optimization algorithm. So they optimize the novelty of their model, they optimize it, and they're able to generate something better. Because if the model fails, there's no reward. If you're able to predict a good maybe drug molecule, then there's a reward. The reward is that it's able to cure a disease and something like that. So if it's not, then it's not able. So we have those applications of reinforcement learning, but just do know that we have right from pre-training, we find that application right there. So you can actually do that. And also I've already spoken about this, but just a little bit about how the flow, the pipeline on how to run this. You have your raw text data, that's your model. You chunk it into tokens. That's you break your text or your inputs into smaller units. It could be words, it could be characters, it could be sentences, it could be all that. You break them into smaller pieces, and that's what we call tokenization. And those smaller units are what we call tokens. I've already explained that. The preprocessing, that's the cleaning, the lowercase, the removing of punctuation marks. You have to do that. Is very important before you proceed, because if you don't do this, it's going to constitute noise to your model. I've already explained that, how you can drop all that. Without dropping them, you will not know your standard tokens, because all those punctuation marks, they are constituting noise to your model. They will not give you the optimal result. Then after that, you do feature extraction. You extract your features, and I mentioned that you convert it to numbers, and that is what we are calling embeddings. We call it embedding. You embed it. That's where you extract important features. Embedding is at this step. You get important features. You learn in biology. You have the function, maybe the function of a protein. You are learning the functions. How rich is that protein? You are learning from, like, you, for instance, you get a foundation model like ESM. We have ESM and different other models like DNA, RNA, bath, and all that. And then you got your model from here. As you got your tokenized DNA RNAs, and then you also have their targets like the proteins. You can actually use the proteins to learn from other foundation models like protein language models, because it learns the language of protein, it understands the language of protein, and you can actually generate embeddings from that, and then you can use the embeddings as part of your input, maybe your encoder inputs. But because we are just starting those more complex things, I wouldn't want to go into more terminologies that may confuse you at that point. But you can actually create more embeddings and use it as your encoder input, and your decoder input will now be your original data. So I can use like my DNA and RNA sequences as my decoder input, but my encoder input is going to be my rich embeddings, which I've gotten from a foundation model. And then you train the model, you pre-process the model. That's post processing, and this is what we are also calling it. You can use reinforcement learning in this step. You can generate molecules. You can do. We have different methods, different ways of generating novel things. It depends on what you're working on. It could be materials in material science. We're trying to generate something, but we have greedy algorithm. We have greedy search. We also have top case sampling. Top case sampling is another method where you can actually use that in downstream to like generate what you want to generate. If it's classification, you want to classify, you can classify. If it's prediction you want to do, you can do. But if it's generation you also want to do, you do. But most times in this NLP, if it's medical images, most times it's classification as well, because you classify, whether they heard the patient and all that. But if it's generating like something new or to cure a disease or something, then it's going to be this. If it's predicting whether the patient has a disease or not, then it's going to be something like this. So these are just some of the things you will learn, and these are just more examples. It's just like an input that you have this input, and then you break it into these pieces. You have like Apple was this Apple company that develops laptops, phones. It was founded by Steve Jobs. Apple was founded by Steve Jobs. This has broken down this into different pieces. And who will tell us this type of tokenization? Is it word tokenization, or is subword, or is it sentence level? In the comment box, you can type it. Okay, word level. All right. Okay, so it's word by word. So, and how many tokens do we have here? We have 1, 2, 3, 4, 5, 6 tokens. So we have 6 tokens here. 6 tokens. And then we have the lowercase, which you can, you have to, pre-process this into a lowercase. Apple is going to be a small letter, and Steve is also going to be a small letter. So you pre-process it into a lowercase, and then you extract the features. That's I mentioned about the vectors. You see the dimension. It could be you can look at the dimension. It is 3D, it's 2D, or whatever. And also NumPy array. And Python doesn't end there. We have a lot of materials on NumPy, or a lot of other things that you can learn, because Python doesn't end there. You have 2D, how to do a lot of things. This is just starting from there. And I think Roland will be taking on more things tomorrow on how you can use the knowledge you've learned on more difficult tasks in supervised and non-supervised learning with also deep learning. So you extract the features. I remember I told you this is to convert numerical features into numerical features. I mean, to convert words or all that categorical features into numerical features. So here you have the numerical features, the rich embeddings, which you're going to feed into your model. And then you feed into your neural network, you train your model, and you're able to predict the output. This is just a clear example. I've given this word embeddings, which is something you quite understand. I don't need to go into this. You can look at it and you will be able to understand the semantics. But it's very pretty. This is pretty straightforward. This notebook, you don't need to all the coding. You can study it, you can understand it, but pay, pay, focus more on the outputs so you understand what is going on here and what we're talking about, like word embedding. What is word embedding? Is to convert words to vectors. And whenever we talk about vectors, vectors is numerical values. It's also is values, just numbers. So this is a 3D visualization. You know, 3D. We have 3D visualization here. So this is it, and then you go over this. We understand it's very easy. It's pretty straightforward. We have word to embedding. That's words to vectors. That's words to numbers. You have these are words, and then you try to convert it to vectors. But because of time, I will be stopping at that. I've already spoken about transformers and attention. I've done that. You understand the basics. This is just an introduction to this course. So it's I gave another example here, which is a very clear example. You have the bank is by the river. What does bank mean here? Bank. The bank is by the river. So in calculating the attention, I remember I mentioned you calculate the attention scores. So how much to focus on each word? So you see here it focus there is just 5%. Bank 20% is 10%. And you just splitted this, and then river is like 45%. The bank is by the river. The river is the main word here. So it focused on this. So if it was in the model, like maybe in a biological sense, we say this is the motif. This is the most important segment. You know what motif means? The most important section. Those few nucleotides in a sequence, they are the most important ones that tells us a lot about that sequence. So we'll say this is like the motif in that sense. But in this way, we'll say it has focused the attention on this. So this is the highest attention score. And then we'll go with this in the model. And I can I can now sort of like condition my model. I'll condition my model on this particular on this particular word, this river, because this is where it has more vital information. And then we spoke about all these language models, which I won't be going into the math and all these things, but I've already spoken about the all the language models and all the fine-tuning and all the pre-training and all the reinforcement learning and everything here. So I'll push this to you, go over this, or pay more attention on this output. You may not focus more on the code. If you can try to understand the code, fine, but it's not even anything difficult. It's just to print things. So, and you learn about all the strings and all the booleans and all those things before. So you should be able to understand when they are doing something in coding here. You should be able to understand whether this is a string or this is an integer or this is that. You should be able to understand that, but that's not the most important part of this notebook that will be sent to you today. This is just the notebook for you to understand the basics of this Gen AI and all the large language models that we've been talking about. So we have more information for you. You go in depth, you read more about this. We've provided you with more links. You go down, you find more links. Our Gen AI capabilities, you also find the summaries. We have everything here. I also provided Hugging Face models. Practice with Hugging Face model. I mentioned this. Google Colab, we've already spoken about that. Hugging Face, I introduced it to you today. We have simple data sets. On Hugging Face, you can find some real world data sets from that and do some hands-on projects using those data sets from Hugging Face. And you leverage on all this. We have a lot of pre-trained models on Hugging Face. You can leverage that. You can build chatbots. You can do a lot of things with those kind of data. And then the takeaways, which I spoke about that before, we have more resources on Hugging Face, on Fast AI NLP. This is a very good GitHub repo. You can fork it to your own and play around it. We have Google Colab, which we introduced it to you before. Papers with Code. Papers with Code. They have a lot of code there. You can go here. And we have archives. You know, we have archives. We have both the general archives, the bio archives, the med archives, chem archives, a lot of archive. Psychology, they also have archive, law archives, different archive. It depends on your field. You will find an archive in your own discipline. Go there and look for papers and try to reproduce the results. That's how you learn. You try to reproduce the results. You have all the AI tools at your disposal. You can be able to query all those things. You have this Cloud Anthropic, which I introduced to you before, and you can also reach out to Ross to talk to Ross about anything you're going through. And the instructors, can we also share the attendance form in the comment box if you have questions. We have referenced the main papers here as well. You go over them, and also the key figures, the father of deep learning, who is leading Jan LeCun. He's leading the efforts on world models on JPA. The JPA, you can follow him follow these people on LinkedIn, see the new updates in the field. On Twitter, follow them and see what is happening in the field. I follow all of them. I've followed these people for a long time, and even people beyond. Andrew Ong and a lot of other people in the space. Yeah, he's right here. You see, he's in Stanford. He has took this class, and we repost a lot of things on our social media platforms as well, especially on Facebook, LinkedIn, and other social media platforms. You will be able to learn a lot from all these resources that I provided here. We provided here. So spend time on that. We hope that this is going to be a starting point, but this is just an introductory class, so that's why we are not spending much time on anything. It's just the basics. We want you to just get yourselves to get you started with all this, so you can be able to do that. If you have a question, if you follow, put a plus. If you have a question, put a minus. If you have a question, you can put it in the comment box. But at this point, we'll be taking the attendance. If you follow, put a plus. If you don't follow, put a minus. If you have a question, ask. Otherwise, we are coming to the end of this session, and we will be taking the attendance at this point. We have the attendance link here. We're going to be sharing it now, and the attendance link is going to stay for a while. We're going to be here even after this session. And also remember, the deadline for the other task is on Sunday. It's not today. I mistakenly said the deadline is today. It's not today. The deadline is on Sunday, so know that the deadline for task one, we extended it. It was actually supposed to be today, but we extended it to Sunday since we released it on Sunday. So you still have more time to work on the task. Now you have access to all the AI tools, the copilots. We believe these experiences are going to get you started, because this you are just in the right place, and we are going to push. I'm going to push the slides and the notebook to you after this call, and then you'll be able to practice and go over them and start following up people. This is how you start. Consistency is very important. And I had one of my roommates who asked me, Joseph, do you study machine learning every day? Do you do it every day? And yeah, he noticed that I study machine learning. I do this every day. So consistency is very important in doing this. Consistency is very important. So yes, the math, you also get to know more about the math. We have a lot of resources on our Facebook. So go on our Facebook. We have a lot of resources. Math of machine learning. We have resources for that on our Facebook group. We repost them on our social media platforms as well, but we try to repost that every week. So we have math of machine learning, and Andrew Ong, he has a very fantastic math of machine learning on Coursera, and you can apply for free to learn on Coursera for free. So I would like to encourage you to try as much as possible to get you started. But for now, just get yourself started, get yourself familiarized with everything. You can learn math or machine learning along the way. We don't want to bother you with all the math. We know the math. We have the resources for math. If you need resources for math or machine learning, I've taken some courses in math or machine learning, some CS classes. I can send you. I can send you to. And if you check my GitHub repo, you may find some materials. I kept them open, so that's a secret. If you can check my own personal GitHub repo. I think I'm still sharing my screen, and my name is also there. You can look me up on GitHub. I think I can just change my account. Um, all right, I don't think it's that one. Let me see if I have my GitHub here. For those of you who want more materials on this, on our New Life Research Foundation, you have a lot of materials too. But on my own personal one, what I do is I document everything. I'm a very good. I document everything. I'm very good at that. If you go through my GitHub repository, you will really find you will find that I really am very good at documentation. So I will copy my repositories. These are my repos. And so here you can see that I have, for those, someone asked about math or machine learning. While you are taking the attendance, if you've taken the attendance, you feel free. We are going to pray before we leave, but that's the end of this. If you have any question, drop in the comment box. But if you check this, you will see some courses I took. You will see protein structure classification. I did this as well. For some of you in that space that you want to, it's a project I did. That was just a personal project I did. So, but if you want to learn that, you see, I was just encouraging you to do personal projects. This was my own personal project I did in 2024, just to get my hands started on anything that had to do with card protein structure classification and all that. So I did this personal project, some are personal project. So, but if you go through this, you will find data structures and algorithms. You will find some assignments and things I did. Graph, you see graph theory. You find data structures, algorithms. You find network X questions. You find a lot of things. You find a lot of resources here. There is this notebook here that for those of you who want to learn math and a lot of things, you'll be able to learn all these graphs, all these plots. Network X. You can be able to pick some things from my GitHub repo. And you see, I started this not too long ago. I documented it like 4 years ago. But if you go back and see you see machine learning for computational biology. I have a lot of resources here. I took this course at Georgia Tech. So you have a lot of materials here, a lot of slides, a lot of things. I'm going to send this link in the comment box. And not only this, I think I do have CS. I'm yet to see some of my CS courses, but I do have more courses I took and documented here. I'm seeing more projects. But you see BME 68. You see this class. I took this class as well. This is biomedical engineering. This is the medical AI class I took. So you will see medical AI class. You find a lot of materials here, a lot of resources. And also you go back to, finally you go back, I'll click next. I have more materials for those in bioinformatics. You also find a lot of materials to get yourself started. But also you see machine learning biosciences. So for those of you in this space, you can also find a lot of materials here. And not only in life sciences, you find like probability and a lot of materials, HMA, a lot of like materials in this space. Not only that, you also go back to programming it for bioinformatics. This was many years ago, but you also find some of my assignments I did. And for some of you in bioinformatics or who are doing something like that, you may want to learn. But you find a lot of materials and also resources that I put here. I put them there to help people. And not only that, I think I have more materials, but if you go through this, you find more tutorials like R programming tasks and also our PRS tutorial. You find more materials in this space. So I'm going to put that in the comment box, but feel free to ask any questions. Otherwise, we are going to be closing very soon, and we'll come back tomorrow. Tomorrow is going to be our last instruction day. For today, you are going to receive your task two. Your task two is due next week. It's going to be more than a week from now, and we also put it on a Sunday. We extend it by 2 days. So yes, so you can be able to work on your tasks. Your task two is not going to be so it's not going to be so different from what we've done in class today. You're going to be I can also people are asking, I can send you the materials if you so wish. In the comment box here, I can forward you the materials, and that was my own. I would have sent it to you right from the beginning. I forgot to do that, but how do I close this? Um, seems it's gone blank. Okay. Okay, so I'm going to be uploading, for those of you who wants to download the materials, um, I will try to upload this notebook, intro to, okay, the notebook, I just uploaded it in the comment box. I wish I sent it to you earlier so you can be able to follow on your own. But all the materials, and then for the other one, I think I have it somewhere here. Okay, not there. So for this as well, you have all the materials. I'm going to put this in the comment box. So we're here to take questions. But once it's almost time, we'll be closing, we'll be rounding up. Feel free to take the attendance. So no, you have to ignore that file because it's not opened where I don't think this is. I don't think that is where you're supposed to open that file. I don't know what type of file is that, and for some of the files, oh, you don't need to open. You can, okay. So for the, I can see the file. You're on task one doc. It may not open there. Remember, this is a Jupyter notebook environment, right? So only things in the format of like MD or something like it. A README file can you can open a README file here, but I don't think text and PDFs. I don't think you'll be able to open them in this workspace. So download it, have it on your local computer, read it, but go work only on the notebooks there. All right. Someone is asking about the link, the attendance link. So, Fred, are you there? Fred, are you there?
Yes, I
All
am.
right. I'll hand over
Yes,
to you.
I'm here. I'm here.
I'll hand over to you. We have just 6 minutes to close, so you take over.
All right. Once again, good evening, everyone. I believe we've been following through every bit of the learning process. I would say this is one of the most interesting sessions for me because I'm seeing a lot of potential in what machine learning and natural language processing can accomplish once you are able to master it. And for some of us, the difference between where we are now and where we will be in the next few years is if we put in the work. If you are able to put in the hard work to acclimatize with the basics, the fundamentals of the entire AI ecosystem. You see, in the course of these sessions or because of these summer uh, lessons that we've been receiving, there are different aspects of AI that have been shown to us. Some people are going to master every one of them. Some will master some, maybe two or three. Some will master two, some maybe just one. The goal here is that you get to that level of mastery that you can always produce result with it. So you don't necessarily need to know everything. But if you can be able to identify one that is very relatable to you and be able to put in the hard work, the time to do personal project. And by personal project, I mean you pick up a challenge or a task and try to get your hands dirty with interpreting that problem and profiling solution using AI. I'll show you after a certain point, you'll get the hang of it and you become a very proficient in it. So I would like to thank our instructor and resource person, Mr. Joseph Lupe, and also Bro Saha Peter, who took us in the morning session for today. I also want to thank the TAs who are in the background trying to answer questions in the comment section, and also every other person who has stayed up until this time. It has shown that, or this is an indication that you really want to make a change and you want to learn. My hope is that it will not be a waste, and that when you leave here, when we come back next year, because definitely we'll be here next year if the world does not end, if Christ tarries, we will be here again and will come with new and diverse aspects of learning that will profit you. So when we come that next year, we'll find you in a different place entirely. You should have, moved steps ahead. Thank you once again, and God bless you. Tomorrow we'll still have another session. Tomorrow we'll start same time, 8 a.m. West African time. We'll have a morning and evening session as well. So just do all you can. Go do your assignments, and the materials that were used to, do the training today is going to be sent to us by email. So download them and try to practice. Okay. Thank you once again. God bless you and have a wonderful evening. So before we leave, we must pray. Sorry, we have to pray because we started with prayer. So this is very, very, very important. I'm going to pray right now, and then after that we can, log off. In Jesus' name. Father, thank you for this wonderful sale that you have brought us. You took us through for several hours. Right now, we've been here trying to share knowledge, trying to move from one level to another. It is your desire for us to grow, and we are taking steps in faith, knowing that you are with us. We pray for understanding. We pray for knowledge, and we also pray for the capacity to retain. I ask, oh Lord, that everyone who has taken part in these sessions for today, Lord, when we leave this place, give us the capability, expand our capacity to learn, to retain, and to execute in the name of Jesus. We pray that as we disperse, those who are going to be moving, Lord, we pray for protection. Those who, wherever we're going to be, Father, may you preserve us. I ask, oh Lord, that you keep us in your arms, and we'll be back here tomorrow again to continue our lesson. Thank you for what you have done. In Jesus' name we pray. Amen. Thank you once again. I'll see you tomorrow.